So, high art, low cost, tips and tricks from the field. I'm a field engineer, which basically means I spend a lot of time sitting in fields of events, fields of developers, boardrooms, basically anywhere where people are using Unity. I kind of spend a lot of time emailing and talking with developers that use Unity to try and help them break into all the new features, work out what they can get best out of Unity and all our services and support. And I work within a team in the UK under Andy Bramall, who has a team of field engineers and evangelists spending time in Europe, European region, basically. And I've been at Unity about 6 years, and before that, 10 to 12 years of games, AAA, console development, that kind of stuff. So it was my job at my last developer, which was Disney BlackRock, to bring in a third-party solution to try and get around the problem of our very resource-heavy core tech group, so that we can actually have an off-the-shelf games engine that we could prototype with. And so I tried a few different engines at the time, and Unity won out. So I kind of became a bit of an internal evangelist for Unity at that stage, and it kind of grew like a sort of organic thing within our organisation to be able to start greenlighting and prototyping interesting games and interactive experiences with the software. So that's a bit about me. What do we do? Well, we spend a lot of time, as I said, at events like this. We've also got Unite, which is a big gathering of all people that are interested in using Unity. They all come together in different places around the world. Our next one's in Asia. We've got Shanghai, Tokyo, and Seoul. And then we've also got Unite in Amsterdam, and then we have a few in the US. So that's the Unites. They're always worth going to. Lots of great talks, parties, that kind of stuff. We do developer visits, so we work directly with customers and people that aren't customers yet, so that we can show them how Unity works, how to do things the Unity way. We do offer training, that kind of stuff, and we kind of engage with their producers and their artists to try and squeeze the best performance or the best ideas out of what they're doing to work with Unity. We also take part in hack weeks, so as a kind of bit of dog fooding internally, it's important for us to know how our software works. And coming from a background of making games and then finding myself not making games for so long, it can be very easy to get out of touch with what the tools do and how they work. So we quite often have hack weeks to bounce ideas around and essentially use our own tools to find out what's working and try and break stuff and QA, things like that. We also do outreach, so we work in schools and universities to teach and talk to people about getting the best out of Unity. So, what do we want in VR? Typically speaking, we spend a lot of time thinking about how we're going to get the best quality, visual fidelity out of what we're creating, best bang for our buck. And when it comes to VR, we're quite tempted to say, well, we've hit the bar here. There's a huge range of different hardware platforms, but at the end of the day, the important thing is visual fidelity, whether it's photoreal or some other look we're looking for. So one of the things we wanted to try and look at when we were doing one of our hack weeks was the idea of taking some content that's designed for a very high-end VR set of kit, so PC, Vive, Oculus sort of level stuff, and trying to squeeze that stuff onto mobile VR so that we can work with mobile phone GPUs and do the similar kind of experiences, but using obviously much less power and cables, for want of a better word. So one of the things we did at a hack week was we tried to squeeze the Adam project. I don't know if anyone's seen the Adam video. It's one of our great tools for promoting how Unity can be used to create very nice looking AAA quality content. We produced a movie with Adam. Most of you guys have seen that. We tried to squeeze that into a VR experience on Gear VR for one of our hacks weeks. Unfortunately, we didn't get very much after the first. Once you've loaded a few models, chucked it all onto a Gear VR build, it was quite tricky to load all of the physically based shading models and stuff. This is a kind of graphical interpretation of what we could do. But the point I'm trying to make here is that we're aiming to convert very high-end content to work with a range of different platforms. Then we need to have a think about how we can optimize those. And the reason for that is that there are a lot of constraints associated with VR. We have to hit some very high frame rates to remove the possibility of feeling rather sick or not, because the movement that can happen when a user is using any of the headsets can be fast enough that you can really, and everyone knows this, has been talks about this a lot, but essentially speaking, many of these platforms have very high frame rate benchmark goals to reach, and you're rendering on 2 eyes, and you're doing reprojection, you're doing all this kind of stuff, which makes VR rendering proposition a costly exercise. So what I'm going to try and do here is try and uncover a bit of the Unity rendering pipeline so that you can understand a little bit about the kind of optimizations that you can make at each of the stages. So they show everything in these slides that take your game from the game loop to the render loop, what's basically being processed. So at this early stage, you're looking at the CPU pre-processing. So you're trying to work out the gameplay, physics, and AI. You're looking at processing transforms of the objects in your scenes. You're looking at which objects are level of detail set up and trying to isolate and load those models. You're calculating the dynamic batching, the CPU skinning, the frustum culling, and the sorting. And so at this stage, the optimizations that you can consider are things like using the culling API. So that's like an array of spheres with callbacks to notify when you're entering and exiting the frustum so that you can turn off things you don't need to render. So you can also expose hierarchy elements from, say, characters which have thousands of bones that aren't actually active. So there's a tick box for optimizing your character hierarchy that's worth taking into account. Also, making use of level of detail. So generating high-res, medium-res, low-res, etc. meshes that can be loaded, switched on and off at runtime is very essential to optimizing stuff at this stage. Funny one to talk about here as well, if you're not actually winning from sorting stuff, then disabling sorting altogether can make a saving. So if you already know that you're not bound by the sorting issues that you can get, then you can disable that and save a little bit as well. So also, if you're not bound by draw calls at that stage, then don't batch. The next stage, we move into the render loop. So we're doing the VR stuff here. So for virtual reality, your stereoscopic rendering, you are essentially rendering cube 1 for the left eye, then for the right eye, then rendering cube 2 for the left eye, and then the right eye, etc. The whole scene twice. So this is where we can make use of stuff like single-pass stereo rendering, which is now enabled on most of the platforms in Unity. It's very important to consider the shadow map computations at this stage as well, because essentially the placing of shadow maps is the position from each of the light that casts the shadows and renders from that point of view. So all the kind of overlaps and additional lighting from here can be very expensive. So the kind of savings you can make here, reduce the shadow casters and receivers, the number of them actually casting shadows, and limit the distances and the cascades. And you can avoid shadow mapping altogether if you like. You can start to do things like blob shadows, really cheap tricks that can make a big difference. A little example here where you get some objects, and if the video play, well, essentially you're placing little blob shadows under things without having the necessity to calculate real-time shadows for all of these elements of your scene. So then we leave the world of the CPU into the GPU, and the golden rule here is to try and avoid changing the state inside the GPU to leave that loop and come back in. Now, what that means is, how do we understand what breaks the state? Essentially, things like material changes, the kind of materials with different light maps, all those kind of things can break those states and cause expense there. So it's important to start thinking about where you can make optimizations here. So material changes, light map changes, spatial localization, where things are placed in your scene affects how things are batched together. It's worth thinking about enabling batching at this stage as well. We've also got texture atlasing, which you kind of consider, especially with 2D stuff, but the way that you put together your scene so that textures from different places within the same geographical area can be batched together into a texture page. Large light maps, one light map per room, is a great example where if you've got objects within a scene that are accessing different light maps, then you can be switching materials and and causing a lot of opportunities to leave that loop. And what you really want to do is to start thinking about using one big light map to do as much as possible rather than lots of little ones, because then you're not breaking the batch here, breaking the state rather. So you've also got the opportunity to use material property blocks. So you can change certain materials of the properties of the material at runtime without breaking the state here. And then we need to consider multi-threaded rendering, and also, if you're going to go fully into it yourself, using the Mesh API to actually draw all the stuff yourself manually. It's above my head, personally. I'm not a programmer. But there are ways to draw lines and draw things to the screen that means that you are the architect of exactly what gets rendered. So, on to the next stage. You're into the GPU-bound zone, vertex processing. You're looking at rasterization, spherical harmonic lights, per vertex lights, and GPU skinning. So, at this stage, the kind of savings you can make really depend on just having fewer triangles in your scene and maybe using CPU skinning instead if you're GPU bound. Moving on to the fragment processing, this is the really expensive part, the moment where you fill the screen with pixels. So if you imagine on the average platform, you can fill a screen about 5 times before you're actually going to drop frame rates there. Then if you're just drawing 5 textures on top of each other, that's your 5 gone, you know, it's your 5 a day if you like. So it's very important to start thinking about the kind of optimization you can make here. So you're processing the shadow maps at this stage, you're processing the deferred lighting pre-pass, the light mapping, and everything to do with the physically based rendering, so your standard shader if you're using that in Unity. So the savings you can make, you basically want to think about limiting the overdraw. So we're talking about things like leaves and particle effects that might be semi-transparent. Try to get away from using a leaf, which is actually just a billboard with cut-out shapes, and try and create something as close to the shape as possible so that you have less and less overdraw with other semi-transparent surfaces. Control the rendering order with material render queues. So you can actually start to control individual objects in your scene and the order that they render. I'll show you some top tips for that shortly. And avoid transparency really altogether if you can. So like if you've got objects that are falling, you might as well make them a mesh. You can do mesh particles in Unity, which is quite handy. You can just select an imported mesh to render your particles with instead of billboard. And then sprite sheet animation, where you're just having one sheet with lots of different stuff on it, can make savings as well. But try and avoid transparency where you can, especially alpha test, because alpha blend is expensive, but alpha test gives the illusion that it's a bit cheaper because it's not such a hefty calculation on the edges. But it actually, all of that transparent space, every time it's overlaid, is costing you in overdraw. So use cheaper shaders where you can. So switch from, say, the standard shader. You might want to just use something like a specular diffuse, something that's a bit cheaper on the target platform. So this is an example of the frame debugger, which will actually show, if I can get the video to play. We should have playable videos here. Let's have a look. Why is that not playing? Yeah, just getting a still here. To cut a long story short, you have all of this information on the left, and you can step through all the individual frames and define where the render order of each of your objects rendering in your scene are. It's a bit tricky, but you can actually tell from, if I could play back this video. I've got anyone to play back the video? Play. We shall come back to that slide later. Effectively, you can run through the draw calls that Unity calculates in real time. I'll maybe switch to a version of Unity in a minute and show you that running. So, on to the next slide. We are finally at the multi-pass stage. So for each pixel, you may have to do a second or third pass. So shadow mapping, deferred lighting, forward lighting, pass, all this kind of stuff happens at this stage. So the savings you can make, we're thinking about decreasing per pixel light range. So that's reducing the range, trying to have, if you've got lots of light scattered around your scenes, then trying to make sure that they don't all overlap. That's a very important thing to think about. And have a max number of per pixel lights that can be constrained within your scene. And even if that's manually setting yourself a limit and removing them later. Again, reducing overlaps, really useful here. So, screen space processing. So this is where all the post effects and stuff happen, and it's, again, very expensive. You've had to do all of this stuff so far in 14 milliseconds, and now you're basically filling the entire screen. Again, if you do that 5 times, that's your lot. So you need to think about the kind of effects you apply here. This is a rough order of expense, in that these are the cheapest, right down to the most expensive. So you've got color grading, tone mapping, bloom, anti-aliasing. Depending on different ways of anti-aliasing, you've got different choices to make depending on the platform you're looking at. Screen space reflections and screen space ambient occlusion getting very expensive at this stage. So trying to calculate the areas that bounce light does not reach to give you the idea as a post-processing stage of darkening the nooks and crannies and corners. So as little post-processing as possible per pixel, and use the new cinematic image effects stack, which we've got, which makes things a lot more efficient. It brings them all into one stack, and it enables you to enable and disable and profile those at will. Now, that's quite a lot to take in, so I'm going to try and create something a little bit more digestible for you guys. So let's start with a recipe for the starter. Enable your batching and dynamic batching. So static batching and dynamic batching, trying to group together objects that are static and those that are dynamic so that the scene knows how to treat those at runtime. Disable your shadow mapping altogether. If you've got ways of cheating, you're talking about blob shadows earlier, other cheats and special ways of doing things. Again, it's all about smoke and mirrors. Just don't try to use smoke or actual mirrors because they're quite expensive. Disable your procedural skybox and any skybox lighting. Just if you can make a picture of something, that's great. Disable your runtime global illumination. It's one of the coolest things in Unity to bounce light in real time around your scene, but it's not always needed to give the impression of lighting in your scene. There's great things you can do with baked lighting. There's great things you can do with cheating and the like. Change all your lights to baked, so you can bake a really nice light map that gives the impression that everything has been set in a nice looking scene. You know, you can trick the eye doing dynamic things that won't notice that certain baked lights have happened there. Change all your emissive shader properties to baked, so that you're not actually emitting bounce light from your shade. One of the great things in Unity is you can use any surface to be an emissive light once you've enabled emissive materials, but it's very easy to forget that you've done that. So go back and check that kind of stuff. And then again, whack the light map size up as big as you can, which would then create less light maps. So you're trying to squeeze as much into one light map as possible. For the main course, let's pre-warm the profiler. This is really important because you want to understand what is costing you in your scene. Then the profiler is the tool you need to use. It's your recipe book for trying to understand what is being rendered and at what cost. So there's a whole load of different tools. You've got the CPU, GPU, memory, profiling, and of course the frame debugger, as I mentioned before, that you can step through step by step. Inspect all the overdraw and use the scene view overdraw mode or a replacement shader so you can see where materials are overdrawing and address those issues. Use the frame debugger to watch through the rendering order, just like my video that didn't work, and change the render queues accordingly so that you understand that if this bit of carpet that's being rendered after the lectern and after all that, then there's a square under here that doesn't need to be rendered at all. You can change the order of things rendering to remove stuff that doesn't need to be rendered. So, is that enough? Well, you're some way towards doing things. So you've made all of the inbuilt, automated and optimizations that you can, but it's still not quite enough to get where you want to be. So then we start to think about the range of perceptions. So we're thinking about the right mesh and the right shader for the right distance. And what that allows us to do is to turn stuff off that we don't want to render, stuff that's expensive. So it's about understanding where the player or the user is in relation to your assets and the things that you're trying to create on screen. So the first range, 0 to 3 meters, this is kind of where you want to focus all your vertices. So you want to understand that the user can see geometry close up. You can't always trick them with fancy shaders really close to the eyes. You just want detail in the mesh at this stage. So 3 to 10 meters. This is where you can use a few less verts, but you can start to use normal and displacement maps. This is kind of the range that's in front of you that actually gives you the visual wow before the backdrop. It's kind of telling you that, oh, I've made a good job of this artwork here. So you want to throw everything at it here, but confined to this range where you can. Then range 3, 10 meters to 20 meters. So start to think about baked shading and silhouettes and things that give you a bit of parallax, but aren't actually going to be fully rendered 3D models with very expensive shaders on. And then the final range, which can pretty much be baking everything out to sky domes or imposters, environment maps, that kind of stuff. And in order to do that, you have to kind of understand the materials that you use at those different levels. So if you're constantly changing between those ranges, then you need to understand what those objects are that move between. In Unity, you have a standard shader, which is what we use to represent physically based shading. So the actual physical properties of materials are realistic, and you need to put in the right values. But the advantage is it works well with the lighting system, and everything looks nice. You get reflections, you get those values. But it uses a lot more texture maps, memory, all that kind of stuff. So it is possible to run fully standard shaded materials on objects in your mobile VR scene, but use it wisely. Use it where it counts. Use it where you can see it. Use it where it's close to you. And then for everything else, use a custom shader that you know is a bit cheaper, that can do the job, that can give the impression of what you want to give. So for this example, we took the Adam model itself, and we are actually able to use the standard shader and the animation, but we decided to remove everything else from the background and bake that into a stereoscopic movie, essentially. I'm going to see if that's just, because that's just a still. The next one is actually a video, but I'm going to try and run through the stages of actually baking your environment. So if you imagine you've got a highly complex scene that's not suitable to run on a certain platform, and what you want to do is you want to turn everything that you have in Unity into the foreground geometry that you load into your project. So you've got your near geometry, your range 1, 0 to 1, and everything in range 2 to 4 you want to bake into your environment. So what you can actually do in Unity is you can position a reflection probe anywhere in your scene, and once you've decided that's the position you want to take it from, disable all the close geometry to that reflection probe, and you can actually bake a high resolution EXR, so a high dynamic range image format, onto disk that you can then use as a environment map loading back into Unity. So the procedure is to pop a reflection probe into your scene, go to the inspector, select the resolution that you want, click Bake after you've made sure it's a custom reflection probe, and then you set the resolution to high, and then it will actually output a EXR file for you on the hard disk, and then you basically hide all your first range stuff so that you've tested it works, and then all your baking is range 2 to 4, and then you have all of the mountains in the distance, the sky, that is all baked into a spherical EXR file for you. So once you've then got your environment map, you can load it into Unity by dragging in the EXR file into another whole project if you need to. Then you remove all the last range geometry, so your mountains, your complex terrains. So this is a very powerful tool if you think about using Unity as a DCC, as a digital content creation tool. Drag in any of the assets you want from the asset store, or high-res models that you've created from 3D Studio or Maya into Unity to be able to use as your paint box, basically, and then do everything you want to with the environments and the skies, and then you can simply bake that out to a texture, which then becomes the backdrop of your mobile VR experience. So the way that you do that is you create a skybox material, and you assign that cube map that you've dragged in. And then under the lighting window, environment lighting, you can also use that material to light your scene. So all the non-directional light from your ambience of that sky dome can be used to even create real-time GI if you want, or to create ambient baked lighting that matches the environment that you've brought in as a baked environment map. So if you don't use the skybox for lighting, then make sure that you set the ambient source to color and the reflection source to custom. Then you've got the ability to light your whole scene from that map. The next stage on from that is to actually, that works very well for dynamic, for static backdrops, so you've got mountains and skies and whatever. But if you're changing the time of day, or there's animation, there's movement, there's dynamic stuff, how can you record that into a static sky cube? You can't. So we start to think about rendering out video cubes, so 360 mono or stereoscopic movies. So we called this, when we did this project, super cheating. There's lots of ways to do it now. People have plugins for rendering out stereoscopic 360 movies out of Unity. So think about Unity as your film studio, where you can actually attach a camera to the head of Adam as he walks along, and he's recording everything in 360 degree stereoscopic motion. You can bring that back into Unity and use that as a dynamic backdrop to what you're doing. So what that tells you is that pretty much anything is possible. If you've got something super high-end, you've got clever physics and animation and FX systems, you can bake all that into the backdrop in video form for what you're doing and create a dynamic experience. Even though it's linear, you can actually interface with the video system to move that backwards and forwards and control jumping from different parts of that video as well. So what we did for that, we took the static environment maps that weren't sufficient for the dynamic environment, and we basically hacked it with stereoscopic 360 video using VR Panorama to bake them out. Things have changed quite a lot now. 5.6, we've introduced a whole new video player component and replaced a lot of render textures. So the video player in Unity. So you can now bring in a whole different format of video, 360 videos, other things, and then we have native file support on lots of different platforms which make use of the codecs that are on different handsets, so H.264, compression, all that kind of stuff. So that's what I'm saying, our new video importer with native hardware support and the video player component. So for that kind of experience, the main difference obviously is that you're not tracking the head. You're looking at Gear VR, you're looking at Cardboard, you're looking at Daydream. You're not actually having that parallax interaction with what's in the near ranges and the far ranges. So in order to make sure that your baked environments and surrounds and video cubes working, you really need to disable the head tracking, because that's not part of the experience that you're making on this platform that we used as an example. So you can do that by simply setting the object scale to 0 on the camera parent game object, which will deactivate any positional head tracking. But again, all the VR stuff in Unity is pretty much a case of checking the VR box, and we now support a whole load of different platforms for that kind of stuff. The future for obviously taking really high-res scenes, there's a lot of ideas to do with photogrammetry. So the idea of taking an existing high-res model and breaking it down into a very low-res model automatically, based on putting a load of cameras around it and basically photographing different views and putting it on a cutout. So the automatic generation of level of detail meshes. This again is a lovely video that I'd like to show you if the videos were playing back on this presentation. As it goes, this particular experiment was our CTO working with Programmetry LOD, where it took an entire village of these huts and then reduced them from over 5 million polygons down to about 5,000 dynamically. So you can load in and out the LODs for these objects and create a very high-res scene with very little cost. So there are a lot of other tools out there. People do manual photogrammetry. So you might visit a site, take photographs of the object from lots of different angles, and then generate multiple different resolution meshes for that object. You guys have probably been there before. But the main thing to consider about that is you then have a mesh for each of the different ranges that can be loaded in and out. And those are pretty much set up automatically in Unity when you load those in via FBX. So for the dessert, we think about using a tasty poly reduction method. There's another set of tools that you can use externally or internally. You might be using Simplygon, you might be using Pro Optimizer in 3D Studio. But the idea is to try and produce multiple resolution versions of your assets so that Unity can pick and choose which to load at different distances from the camera. Reduce your texture sizes and atlas them wherever you can. Limit your shader variance and the number of expensive shaders that you use, and try and use LOD groups, as we explained before, wherever you can. Sprite sheet animations instead of many different particles, so you're picking and choosing from the same. You can actually batch all of the particle effects from one particle into one draw call if they're sharing the material. That's very important to understand. And when it comes to effects like stones and hail and whatever, it can be much more efficient to actually use meshes on a mobile platform than actually using billboard particles. So, at the end of the day, we skip on too many slides. We can do it. The example that we had here, we had the whole of Adam. It was a very, I have to say, it was a very unpleasant VR experience indeed, because what's happening is that you're walking through with Adam with these stereoscopic rendering around you, and you have no control over where he's moving. But it tested the theory that you can generate the AAA high-quality stuff that was rendering on a super high-end machine down to stereoscopic backdrops with an animated 3D mesh with physically based shading in the foreground. That was what we were trying to prove, not that you'd actually make a nice experience from being the prisoner Adam stuck inside his head. And you can do it even better now in 5.6. So we have a new video importer with native hardware playback support on a number of different Android, iOS platforms. We've added Vulkan support for OpenVR. We've also got native cardboard support for iOS using Metal and OpenGL. And we've got single-pass stereo rendering support added for Gear VR and Google Daydream. And that's really powerful stuff. It saves a lot of render time. So the conclusions from the experiments that we kind of put ourselves through is that there is a massive range of performance targets within VR, from supercomputer, top-end, triple GPU, 10 billion GPUs, right down to sort of pocket calculator level. Everyone's having a go at VR. There's lots of different hardware targets. So try and define the target earlier so that you can focus development on whether you're completely rebuilding all your assets, doing certain optimizations and doing some cheats on the background, or you're just enabling batching and trying to make the best of the inbuilt optimizations in Unity. So that will help you determine the balance between optimization, smoke and mirrors, and then fully re-authoring of assets. And as I said before, please don't use actual smoke and mirrors because it's quite expensive. There's lots you can do to cheat and to hide things, but at the end of the day, profile what you do and try and understand where you want to position on this line before you start the project. And you can save quite a lot of time. And at the end of the day, have fun in Unity. Thank you very much.
Great. Does anybody have any questions? Hopefully, fantastic. Yeah, the first hand I saw up was the guy in the, I think it's blue. I can only really see a silhouette. There's a microphone for you.
Hiya. Quick question about mobile VR. You said about making your light maps as big as possible. Just out of the air, what's the maximum texture size you'd recommend for mobile? On desktop, it's like 8096 or something like that.
4096 is kind of where we're headed. There's some, I think the S8 and S7 probably support up to 8K, but for generic stuff, light mapping especially, aim for 4K because that's a good solid amount that will try and build as many light maps into one as possible. There's quite a lot of tutorials on the Learn section of the Unity site which will specifically direct you how to optimize light mapping for Unity. There's a tutorial of about 6 pages. I really recommend anyone goes through it. And it kind of teaches all the basics of not just baking light maps, but how to do real-time GI and how to set up your UV mapping, light map unwraps for all that kind of stuff very efficiently.
Great. Got time for a couple more questions, hopefully. Is there anybody out there? I can't see any hands going up.
If you want a copy of the presentation, get in touch with the crew here. I'll try and send out the slides because there's quite a lot to take in, quite a lot of information. I hope I've done it justice. Thanks, guys.
Brilliant. Thank you very much.